today's lecture, we will cover the second half of Chapter 17 and discuss aromatic compounds. There are also examples of aromatic rings that include heteroatoms, and most commonly for this we will see nitrogen. Here are two examples, pyridine and Parole. First we'll look at pyridine. In pyridine we have 5 carbons in the ring and 1 nitrogen. If we look at this orbital diagram, we can see here the p orbital on the nitrogen is overlapped with the p orbitals of the 5 carbons, and we have 3 double bonds that are in this ring. So the 6 electrons in the 3 double bonds will all be located in these 6 p orbitals. The lone pair on the nitrogen is actually in an sp2 hybridized orbital, and it's orthogonal to the p orbitals. So this lone pair on the nitrogen is not part of the electrons that we count towards aromaticity. If we look at Parole, in this case we have only 4 electrons that are coming from pi bonds, but the p orbital has the lone pair of electrons in it. So our total electron count in the p orbitals for these 5 atoms is 6 electrons still. So this would qualify as aromatic because we have 4 electrons that are coming from the pi bonds and 2 electrons that are coming from the lone pair on the nitrogen. And then in this case we have the hydrogen that's in that sp2 orbital. If the lone pair is necessary for aromaticity, it will be included in the Huckel number for pi electrons, and that means it must be in the p orbital. So in this case, for pyridine, the lone pair does not count because it's in an sp2 orbital, but for Parole, it does count because it's in a p orbital. Depending on which orbital the lone pair is in, it'll also determine how basic that lone pair is. Since the lone pair of the pyridine is not part of the aromatic ring, we'll have a pKa of about 5.2, and so this would be a very basic lone pair. The conjugate acid has a pKa of 5.2. For Parole, this is going to not really be basic at all, and that's because the lone pair is tied up in that aromaticity. So aromaticity, we talked about last lecture, is a very stable interaction for the molecule. And so if we have this nitrogen lone pair act as a base and protonate, then we break aromaticity. And so this is going to be an unfavorable interaction. You can see the equilibrium is pushed far to the left. This is unlikely to occur. And we can see that a little bit further when we look at the electron density of the electrostatic potential maps. In pyridine, our lone pair is localized, and we have a red on the electrostatic potential map, meaning that there's a buildup of negative charge here. This is basic. It's going to act as a base and deprotonate, whereas for Parole, the buildup of electron density is throughout the entire network of p orbitals, and the lone pair is delocalized. We can also draw resonance structures with Parole, where we move those electrons all the way around the ring, whereas for pyridine we cannot draw those. We also have polycyclic compounds that can be aromatic, and so for these compounds we can count the electrons. These compounds are all flat, so we'll have overlapping p orbitals for these. And so here are a few examples of aromatic polycyclic compounds. And we can compare the heats of hydrogenation of these molecules to look at the stabilization energy. As the ring gets larger, the stabilization energy increases, but if we compare that to the stabilization energy per ring, it stays roughly similar to around low 100s in that range. So when we looked at resonance and we looked at radical reactions, we discussed briefly the benzylic position. The benzylic position is the carbon that's attached directly to the benzene ring. So in this case, on this molecule, we have two positions that are the benzylic position. The benzylic position has very unique reactivity because it's attached directly to the benzene ring. The benzene ring is going to pull electron density away from the benzylic position, but also has the ability through its pi bonds to stabilize a carbocation there with resonance. So aromatic rings and alkyl groups are not easily oxidized. We look at the Jones conditions for these reactions. We cannot create a carbon-oxygen bond with just the normal Jones reagent conditions for a benzene ring or a regular alkane or alkyl group. But molecules that have a benzylic position are actually readily oxidized by chromic acid. So this position, the benzylic position, we call activated. It's an activated position. And so this reaction will proceed where we can oxidize the molecule up to benzoic acid using Jones reagent. So this is a reaction that you should know. In order for this oxidation to occur, though, the benzylic position will need to have at least one proton attached. So here we have a quaternary carbon with no protons, and so this reaction does not occur in this case. And we can also use potassium permanganate, another oxidant that we looked at in chapter 12, to oxidize up to the benzoic acid. The benzylic position will readily undergo a free radical bromination. This is a reaction that we actually looked at in the radical chapter. But once again, this position is very activated and it will stabilize a carbocation or a radical intermediate. So we can use this reaction to synthesize a benzyl bromide. NBS is a source of bromine radical. And benzyl bromide itself is a synthetic intermediate because this is a very good leaving group as well. The benzyl bromide will readily undergo an SN1 substitution reaction, and here we're going to start looking at reactions at the benzylic position, and that's because this is a good leaving group, and the carbocation that would form here is going to be stabilized not only by it being a tertiary carbon, but also by the electron donation ability of this benzene ring. So we can easily convert a benzyl bromide, for example, to the alcohol. And if we have a sterically unhindered benzyl bromide, it'll be an extremely good substrate for an SN2 reaction. We can also perform, based on the conditions, elimination reaction, E1 or E2 reaction from a benzyl bromide. Overall, these are just really good leaving groups, benzyl bromides. We can take benzyl alcohol, tertiary benzyl alcohol, and under sulfuric acid conditions, prepare the E1 elimination product. So there's a variety of different reactions that we've already looked at. These are review reactions, SN1, SN2, E1, E2, radical brominations, but it's important to put these in the context of the benzylic position because the benzylic position is just a really reactive position and allows for a lot of this chemistry to be performed directly next to the benzene ring. It's actually quite difficult. So we're going to look at the reduction of benzene, which is actually quite difficult. Under forceful conditions, we can reduce benzene to cyclohexane. But let's just take a look at these conditions. 3 equivalents of hydrogen, that's not too bad. A nickel catalyst, that's not too bad. 100 atmospheres of pressure and 150 degrees Celsius. So in order for us to reduce benzene, it takes a lot of energy put in. Reduction at the benzylic position is actually not that bad compared to reduction of benzene. So we can selectively reduce an alkene. Here, this is an example of a benzylic alkene using platinum and hydrogen, the standard reduction conditions we've looked at, and it won't touch the benzene ring. So what this is telling you is that the double bonds in the benzene ring are safe from our standard reduction conditions that we use for alkenes. There is a reduction that we can use for benzene called the Birch reduction, and this is from chapter 9.5, using sodium and ammonia methanol. And so this will convert the benzene to a diene, accumulated diene, and this mechanism will be is similar to the mechanism that we saw in chapter 9 for this reaction. First, we'll have nucleophilic attack by the sodium, and that will form a radical anion intermediate. You can see the electron pushing here. Then a proton transfer will occur, and then finally a radical. The radical then can undergo a second nucleophilic attack to form another anion, which will then be protonated with methanol to generate the isolated diene. It's important to note that the Birch reduction won't completely reduce the benzene ring. We're going to reduce only 2 carbons to sp3, while the other 4 carbons will remain sp2 hybridized, as well as 2 double bonds remaining in the molecule. We can force the regioselectivity of the Birch reduction by having an electron donating alkyl group in a specific position. So if we have an alkyl substituted benzene ring under these conditions, we will obtain the product that is the more substituted alkene. So notice here we have a tri-substituted alkene. We will not observe any of the product that has 2 di-substituted alkene. And this is because the electron donating group destabilizes the radical cation, and the reduction will not occur at a carbon that possesses the electron donating group. If we have an electron withdrawing group, such as a ketone, an aldehyde, carboxylic acid, or a cyanide, cyano group, then we're going to observe the opposite regioselectivity. So in this case, the electron withdrawing group will be at the resulting sp3 reduced position, and we won't obtain the tri-substituted alkene.